Given the graph of the derivative function, y equals f prime of x, sketch the original function. Okay, this working backwards is something we'll get heavily into in Unit 7 using a tool called the antiderivative, but we can start thinking about it right now. If you know something about the derivative of a function, can you figure out what the original function looked like? The answer is kind of, but not completely. And here's what I mean by that. Actually, I'm going to line up these axes underneath theirs. Let's see what we can deduce here. So this graph shows you the slope of a function. And so when the slope is really low and negative, it means our function is going steeply downhill. In other words, it's decreasing rapidly. When the derivative is negative but not all that big, it means our curve is a bit downhill. What's happening right here? This is a point where the derivative is precisely zero, and when the derivative is zero, it means the slope of our curve is zero, which means our line must be exactly flat. Then the derivative goes positive, and at first it's not all that big. If the derivative is a little bit positive, then that means our curve is a bit uphill. And as the derivative gets bigger and bigger, that means that the function is increasing faster and faster. So this is, I'm going to call this steeply uphill. Now, what would you call it if a function is downhill, as in decreasing, and then flat, and then uphill? This means the function's coming down, and that's flat, and then it turns around and comes up. There must be a local minimum right there. We've seen that behavior before when we were getting signs for our derivative. When it went negative, 0, positive, that meant a local minimum to us. So right here at a comma 0, this point, that has to correspond to a local minimum. And so the curve that we're looking at would have to have a local minimum there, and it would then increase faster and faster. And on the left side, it would decrease quickly at first and then slower as you get closer to the center. So this curve could certainly be a parabola or something like it. Now, the trouble is we don't know where this parabola is. It could be there, it could be translated 5 units up or 2,000 units down. Having information about the slope doesn't tell you anything about the position of a quadratic. Because if you have a quadratic that looks like ax squared plus bx plus c, that's just a general quadratic. When you take its derivative, you get 2ax plus b, and this gets lost. Its derivative is 0, and so if you're just looking at the derivative, you don't know anything about what this c value was, and there's really no way to get it back. And so if you were sketching the f of x, you'd have to say the original function was some kind of u-shape, maybe a parabola, but I have no idea what its y-intercept was. So what you get here is a set that's called a family of curves that are identical in every way except for their position, or except for one parameter, c. And any one of those could have been our original f of x. So when they say sketch the original function f, that's a little bit unfair as a request. We can sketch some possibilities for the original function, but there's no way we can nail it down.